Y'all ready for math? Y'all ready for math? Welcome back, children. Pre-calculus honors. I know you're waiting all day for this lesson. These videos just symbolize like my descent into madness during this quarantine right here. So I'm glad that it's all on record here. So here, start with some do problems, okay? This right here is the integral from ln1 up to ln2 of e to the 3x with respect to x. ln1, I know I drew the 1 a little bit weird. That's just because it'll look like absolute value n if I draw it the normal way. And here's our other problem. So pause the video, copy those down, try them out. And now we're back, okay? So this guy right here, number one, it's actually a cool type of situation here. There's two different ways to do this. Let's do this the more, traditional way first. A lot of people would probably say, you know what? It's not basic integration, right? Because the argument of e is not one single letter. Let's force it to be one single letter. Set u equal to 3x. We get du over the derivative of u is equal to dx. And remember, they call it U-Substitution. With the definite integral, they should really call it tres substituciones. Just remember, the ln of 1 is equal to 0, right? So that's really the integral from 0 up to ln2. Just be careful that 0 is an x value. What does u equal when x is equal to 0? Oh, it equals 0 as well. That's what we call the lusciousness, okay? When 0 is a bound and it remains to be a bound. This might bother you a little bit, right? If x is ln2, the upper bound becomes 3 ln2. A lot of different things you could do there. That's really the ln of 9, the ln of 8, isn't it? The ln of 2 cubed. And that'll be useful. We'll talk about that in a second. Now it's e to the u. There's our second substitution. Finally, a third substitution. Take out the dx. Replace it with a du over 3. Okay, so pull out that 1/3. And now you're just integrating e to the u with respect to u, which we know is e to the u. With all due respect to u, we don't put the plus c. The plus c's, remember, they cancel out when you subtract the plugging in the lower bound from the plugging in the upper bound. We did that the first day. 0 right here. I'll actually make 3 ln2 into the ln of 2 cubed. You should be able to manipulate with stuff like that by now. That should be pretty easy for you. Why would I bother with something like that? Well, now when I plug in, and you could leave the 1/3 attached to the e or not. It's really up to you. I'll pull it to the side this time. I think yesterday I left it attached for a problem. Plug in the upper bound. Remember, ln of 2 cubed, that's really ln 8, right? So that's e to the ln 8 minus plug in the lower bound, e to the 0. Just be careful. You know when, e to the ln 8 is 8. That should be easy. Minus when you plug in the lower bound here, I know it's 0, and we love 0 as a bound, right? But it doesn't always mean that you get a 0. E to the 0 is actually equal to 1, so just be careful with stuff like that. And now you can see we actually end up with 1/3 times 7, so that's going to give us 7/3. Okay, great way to do this problem. Look, U-Substitution, nothing wrong with doing that way as well. Or you could mentally integrate. This is actually a great mental integration situation. Probably the best mental integration situation is when you have e raised to a linear. It's the easiest type of situation because when you integrate, you're going to get back e to the 3x, okay? But just be careful. Don't multiply by 3. That would be the derivative of e to the 3x. Remember, for integrals, you want to divide by the derivative of the inside, so divide by 3. And now evaluate it from ln1 up to ln2. What's the advantage of this? Well, now you don't have to worry about changing the bounds, right? Okay, so there are some advantages. And then you could say e to the, here's where things get a little annoying though, right? If you take out that x and replace it with an ln2, e to the 3 ln2 over 3, minus, we know this is 0, right? E to the 0 over 3. So here you actually have to have the wherewithal to be like, hey, I want to get that e and that ln together and have them cancel out. Come on, remember early in the year, I just gave you problems like this and I was like, simplify. Why do you think, simplify, fly, I can't even speak. Why do you think I wanted you to simplify something like that? For these moments right here, so it's not an issue for you. I'll take the 3, put him back up like he's cold. Brr. All right, we have e to the ln of 2 cubed over 3 minus 1 over 3. And e and ln cancel out. 2 cubed is 8, so 8/3 minus 1/3, which gives us the 7/3. Okay, so there are multiple ways to do these problems. You couldn't see the end of that. There it is. Pause and look at it if you need to. I think the first way is best, but the mental integration in certain situations will be more useful. This one over here, number 2, it's a classic U-Substitution situation, right? The base of a numerical exponent is not equal to one single letter. So I said u equal to 2x plus 1. You could easily double bubble this thing and make it into basic integration. I don't know if that's going to make it easier or more annoying, okay? So really, it's kind of like a case-by-case thing. Some people in calculus are like, oh, I always want to do this, I always want to do that. It depends. You kind of have your collection of weapons, of ammunition, you know, and then you handle each situation differently depending what kind of situation it is. Anyway, so here, let's perform those two substitutions. Actually, tres substituciones. Okay, we can see that when x is -1, what is u equal to? 2 times -1 plus 1, -2 plus 1 is -1. Whoa, that's weird. The old bound was -1, and the new bound is -1. Crazy stuff. When x is 1, u is going to be equal to 2 times 1 plus 1. That's 3, so at least that one changed. Then we got u squared. Take out the dx, replace it with a du over 2. We almost have that equivalent integral as long as you pull the 1/2 to the side. I'll even write it this time. I don't usually put this step in. Okay, but really we have an integral right here that's equivalent to our original integral, okay? And on the AP exam, sometimes it's like a part 1 problem. They want to know which of the following is an equivalent integral. It's not just about evaluating and getting the answer. You want to handle everything here. Let's integrate u squared, u cubed over 3. Evaluate it from -1 to 3. So just like before, we could leave the 1/2 there or pull them to the side. How about we leave them there and even do 1/2 times u cubed over 3? What is that, u cubed over 6? Supposed to be a 6 right here. And you could even pull the 1/6 to the side here or leave the 6 down here. Let's leave it, okay? 3 cubed, 27, 6 minus -1 cubed. So check this out. When you cube a -1, you get a -1 back, okay? So I don't know if you want to write... It's kind of silly to write it this way, okay? I think a lot of people just realize, you know what? We're subtracting a -1/6. So if you subtract -1/6, you really just add 1/6, regardless whichever way you actually want to set it up, okay? And that gives me my 28/6, which we know this is the same thing as 14 over 3. Multiple choice, they'd have 14 over 3. Free response, you could leave the 28/6. Free response, you could leave this. You could leave this right here, okay? So hopefully a little bit easier, both of those problems. You know, kind of, we've been doing 2 definite integrals a day for a while now, and I hope you notice that they've actually gotten easier. Not all of them are as filthy as you think, okay? And, you know, certainly be ready for some of those on your quest that you're going to have assigned Thursday after that lesson, then have Friday to do it. You'll also be given some more definite integrals. You know, we're not quite done with that. Hopefully the homework wasn't bad. You know, number 17, very similar to the one that we did in class. Okay, I set up my bounds right here, stored them in for letters, set up those 2 integrals. Practice stuff like that. It actually shouldn't be too difficult to do, but you have to practice. Number 19, nice little problem as well. What's weird about this problem? Nothing really, okay? You know, you could have done this. You could have said f of x is ln x and g of x is x minus 2, then did, you know, f of x minus g of x. That way you don't have to worry about these parentheses. Lots of different ways to do it, okay? Here you need to get those bounds, calculating the intersection points, the x values and the intersection points, just like over here. You know, it's not always that way. Sometimes over here, they might just say these 2 regions, this little sliver of a region and this region, they want those areas. This guy would start at 0, right? And he would end at C. 0 is not the x-coordinate of an intersection point, so sometimes it's not just the intersection points that are your lower bounds and your upper bounds. Let's do one more. Let's do this. In that integration packet, let's go to number 21. Winner, winner, chicken dinner, blackjack, 21. Let R be the region enclosed by the graph of y equals the square root of the quantity x minus 1, the vertical line x equals 10, and the x-axis, find the area of R. This problem is on an AP exam. I forget which year, but I will tell you that year on this particular problem, they were allowed to use the calculator, yet I'm not allowing you to use the calculator. Why is that? Because I'm a mean, grumpy old man who despises everything? No, that would be the answer if this was a chemistry question. You know, look, there's actually a part, this is part A of the problem. There was a part B, a part C. Those are the parts that the calculator is necessary for. You don't need a calculator for something like this. And you should think about that in the AP exam. You know, do you always need to put stuff in the calculator? Sometimes you burn a lot of time in the calculator. Obviously, you want the area of region R. It's nice to know what the heck the region looks like, okay? And they say it's specifically enclosed by the graph of this guy right here. Also, the vertical line x equals 10. They even tell you it's the vertical line because some people think x equals 10 is horizontal. Crazy. And the x-axis. The cool thing about that is actually if you even use the calculator, you can't graph a vertical line in the calculator unless you use parametric equations, which you'll learn about in BC calculus next year. Won't even learn about it in AB. But you could easily graph y equals square root of the quantity x minus 1. Come on, we talked about this in, what was it, chapter 4 earlier in the year, transforming basic functions. This is y equals radical x. We know what y equals radical x looks like. We're getting inside the argument. We're directly affecting the x-coordinate by subtraction. That's indicative of a horizontal shift to the right. Remember, it's always opposite. So this is just really y equals radical x shifted 1 unit to the right. So here's y equals square root of the quantity x minus 1. This is an x value of 1 right there. The vertical line x equals 10. Well, you go all the way out to an x value of 10. Draw that vertical line through it right there. There's x equals 10. Don't forget, they also said the good old x-axis. That would be y equals 0 right here. So where's my region? Okay, he's bounded by this guy right here. That function, also this vertical line, and also the x-axis. So there he is right there. And it really is the area between two curves. If you want, you could realize, hey, I'm just getting the area between y equals square root of the quantity x minus 1 and the x-axis. So you could just integrate that, okay, if you want to, because your the region actually is above. I think it's better if you see area. Think about area between two curves. Draw that sample rectangle. You might think it's silly, but remember, we only draw one rectangle, even though we imagine like an infinite amount, or like 7. And you can see the upper function will always be the radical. The lower function will always be the x-axis. So you could say area is equal to integral upper function, square root of the quantity, x minus 1, whatever y equals, right? Minus the lower function, which we know is y equals 0. And some people are like, Roberto, I just want to do the integral of the square root of the quantity x minus 1 with respect to x, because I'm getting the area between a function and the x-axis, and the region lies above. That's great. These are equivalent, okay? There's no difference right there. But I really think you should start by setting up this one right here. We need bounds, but the bounds are kind of cool here, right? Leftmost x value of the region, this is the leftmost point of the region. His x value is 1. The lower bound is 1. There's an infinite number of rightmost points of the region, right? But all of them have an x value of 10. So it's really the integral from 1 to 10 of square root of x minus 1, the quantity, with respect to x. And I ask you, can you set that up? Thumbs up, thumbs down, sideways thumb. Make sure you're voting. Let me know if you're struggling on this stuff, okay? Let's integrate. I'll go U-Substitution, say u equals x minus 1. Even though it's a really cool mental integration situation because the derivative of the inside is only equal to 1, so it's pretty easy. But, let's stick with this right here. The bounds become great, right? Because the x equals 1 becomes u equals 0, and x equals 10 becomes u equals 9. And this is really u to the 1/2, right? Instead of radical u. And then I didn't even finish this. Du over the derivative of u, which I said before was 1, is equal to dx. So it appears that du is equal to dx. You could just take the dx, replace it with a du. Pretty easy type of situation. And the bounds are perfect squares, which is luscious. Because when we integrate u to the 1/2, add 1 to 1/2, we get 3/2. Rourke is over here dividing by 3/2. The rest of us multiply by 2/3. And let's evaluate it now from 0 to 9. I know I make fun of Rourke a lot with that division thing. I like to pick a kid each year that kind of mess with a little bit. Normally, I would pick Patrick Getz, but I don't want to give him the satisfaction of even being mentioned on the video. Already, I didn't want to mention him that one time. I'm just kidding, Patrick. So over here, leave the 2/3 attached or pull it out to the side. Maybe pull it out this time. 9 to the 3/2 minus 0 to the 3/2. And we have 2/3. But I don't know how to do 9 to the 3/2. Don't take AP calculus, okay? Please. I mean, you might be saying that that's me being rude, but what would Harrington say if he didn't know how to do 9 to the 3/2? He wouldn't say anything. His eyes would just become red and then shoot lasers out in you, and that would be the end. The square root of 9 right here is going to be 3 cubed, 27 minus 0. So this is really 27 times 2/3, but we can simplify that rather easily. Divide by 3 top and bottom. So I really get 2 times 9, which is going to be 18, okay? So hopefully not too terrible. Short little lesson today, nothing too crazy. Try to give you guys a little bit of a break. Make sure you try your homework, okay? So it's really just more combined problems, right? Practice with definite integrals, okay, mechanically, and then certainly also area between two curves is big, or even just the area between a function and the x-axis. Don't forget about that. That's what we started with. Area between two curves is better, because if you try to do the area between a function and the x-axis and the region is below the x-axis, you're actually going to get a negative answer. That's all we have for today. Okay, that was Tuesday. Tomorrow is Wednesday, and we're rocking and rolling, folks. It's June. Hope to see you all soon. Have a happy and a healthy. Adios.